Now, even though I said area under a curve was a bad way of explaining integration, it is also a good way and a very useful thing that it can do, and I'll show you why. Here, I'm going to go through an example and show you how, what really it means when you say area under a graph. I'm going to try and make an example that makes more sense. So here, I've said, what is the area of this circle with radius 3? Imagine we don't know any formulas for the area. Okay, so imagine we live in a world where we don't know the formula for the area. Well, how can we think about this? How could we dissect this problem to make it easier for us? Well, if we cut up all the circle into lots of different rings, all with different radii, what we could do is we could lie them out. Flat. Okay, we could unroll them, and we know that the circumference of a circle is equal to 2 pi r or pi d. So knowing that, so what we could do is you could just roll out lots of different rings, right? And then we need to think about the area of a ring, all right? So going back to what we think about before, we'd make sure that each ring was the same width, and that width would be this dr, okay? But every ring rolled out, every segment would be a different length, okay? Because they get longer and longer and longer and longer as they move out towards the end. And that means you could have an area for each ring, okay? Now obviously when you roll them out, it's not a perfect square, but for this example, we're going to say it's near enough. So you'd have something like your an is equal to 2 pi r n times dr, which basically means that the area of any one segment is going to be equal to 2 pi r times its width dr. Okay, so hopefully you're still with me. So moving on. Okay, so imagine we took every little segment and we laid them out like this along the x-axis, and they just kind of stacked up from the shortest to the longest. Well, what we could say is, because we know that the length of one segment is equal to 2 pi times r, and you just stick them here, we can say that this line here is equal to y is equal to 2 pi r, okay? So if we wanted to figure out the area of this, you might see that this here forms a triangle, very beautifully drawn by myself, okay? And we know the area for a triangle, right? Because that's area is equal to half the height times the breadth, okay? So the total area will be the maximum height and the maximum breadth, right? So here we can say the height is going to be equal to 2 pi r, okay? Because we see here y is always equal to 2 pi r, and then we're saying if we choose the maximum r, we're just going to call that r as well, okay? That will give us p equals r, so we're left with 1 over 2 times 2 pi r times r, which gives us area equals pi r squared, right? Which is the equation for the area of a circle, and that's where this equation comes from, okay? That's how it's calculated, it's how it's worked out from first principles. So obviously this one is fairly simple to work out, okay, because you can turn it into a triangle, but it's not always going to be the case where that it's going to be some simple shape like a square or triangle where we're able to work out the area underneath it. And that's where integration comes in, allows us to figure out the formulas for the areas under the graph so we can learn more information. So I hope that makes sense. I hope you can see where that came from and what that really means when we talk about area under the graph. It's transforming graph into another way to make it simpler so we can figure out whatever it is we want to know.